where do you find that if the molecule is symmetrical, then even the molecule has polar covalent bonds, but as a whole, the molecules are not found to be having any molecule does not have any dipole moment. So I have given you several examples. Okay, so let us discuss some more points. All right, let us take the example of now. So we have found that carbon dioxide dipole moment is 0. But let us then take sulfur dioxide. In sulfur dioxide, dipole moment is not equal to 0. Why? In sulfur dioxide, you find sulfur has 6 valential electrons. All right. So out of the 6 valential electron, 4 is being engaged in bond pairs, and this is the lone pair. See, this is the orbit in which the electrons are. All right. See, sulfur is a polar molecule because in that case, see, between oxygen and sulfur, which is more electronegative? Oxygen is more electronegative. See here. And in this case, is a resultant. This lone pair also has a moment, but this is less than this. Okay. Sulfur dioxide is a polar molecule and has band structure, band or shape. So in that case, you will find dipole moment is not equal to 0 divide. Let us take the example of H2O. I have been telling you what is the polar molecule. Then how to prove what is the polar molecule? Water is a polar molecule and has high dipole moment. Why you know? See here, water has how many? Oxygen has how many electrons? 6 electrons. Out of this, out of the 6 electrons, 2 are only participate in bonding, and you have 2 lone pairs. Now see here, this hydrogen and hydrogen. Oxygen is more electronegative. The bond moment will have in this direction. Okay, and this is the resultant bond moment. And because of these 2 lone pair also, you will also have a bond moment. So both of them are in the same direction. Because of that, it is having a high dipole moment. Draw. Now, you have a textbook question is there. Suppose you have taken here NH3. This is called ammonia. NF3. So what should be the name? Is nitrogen trifluoride. nitrogen trifluoride. Okay. Now see here. This is N. All right. And this is the loan. And this is okay. Now it is found. See, nitrogen fluorine bond is extremely polar. And in that case, it should have very high dipole moment. Because see, this is the nitrogen, this is fluorine. Okay, I'll show you like this. This is nitrogen, this is fluorine, this is fluorine, this is fluorine. So the bond moment will be in this direction. So what is the resultant bond moment? Resultant bond moment should be in this direction. So all of them are in the same direction. So in that case, you should have a very high dipole moment. Okay. See here, but you will find this very strange. And this is 0.20 divided. So it's very strange. We find in that case ammonia is more polar than nitrogen trifluoride. This question is there in your book. Yeah, just change the sign. See here. So this. These are the bond moment. These are the bond moment. And this is the resultant bond. Okay. And for this one, it is in this direction. Okay. So now see here. Is it not this is opposing this? Yes, because this opposes this, the value is less. But let us see in case of the nitrogen is more electronegative than hydrogen. So it will be in this bond moment will be in this direction. Okay, this is a bond moment. So resultant bond moment will be in this direction. And this moment also will be in this direction. So it is added and it is subtracted. As the effects are added, so value is more. And the effect is subtracted, the value is less. First you draw. Achha, now we'll write the question. Dipole moment. Dipole moment of ammonia. Mu is equal to 1.47 divide is much higher than the dipole moment of nitrogen trifluoride. Then F3 mu is equal to 0.20 D. So first you draw the structure, then we'll write. Ammonia is greater dipole moment than NF3 because in ammonia the resultant dipole moment. See, in exam, if this question comes, don't write RBM. It's because the space is not there because of the arbitrate. This is not the abbreviation of this one, okay? Don't make your own abbreviation. I had to write because space is very less. Resultant dipole moment lies towards the lone pair. While in case of NF3, it is in the opposite direction. By knowing the dipole moment of the molecule, how does it help us? Like applications of dipole moment. Applications of dipole moment. So first of all, what we can explain the polarity of the molecule. We can explain polarity of the molecule. How did you how you can explain? We know that carbon dioxide is non-polar. We can explain why sulfur dioxide is polar. We can explain it by this. Okay. Again, ionic character. Ionic character of molecule. Sorry, covalent molecule. See, covalent molecules are not supposed to behave as salts. But with the help of dipole moment, if it behaves, then immediately you can say that it is a polar molecule and it has a very strong polar bond. Ionic character of covalent molecule, we can explain. Okay. Third, geometry of the molecule. If you know, then you can find out the geometry of the molecule. See here, carbon dioxide is non-polar. Why? Because it is having a linear geometry. Linear. Why? How do you know? Because we know one bond moment cancels the other bond moment. while sulfur dioxide is banned. Why? Because it is polar. See here. In this case, yes, because it is mu is equal to 0.0d, and here mu is not equal to 0. Why? Because we know that in this case, this molecule is polar because of this band structure. Okay. Similarly, we know what is the geometry of the water. Geometry of water is also band. See here. H2O is band. See here. This is the resultant. See here, it's bent. This is bent. Bent or V-shaped. Okay. All right. Then fourth, distinction between cis and trans structure. So I don't know that you have read this one or not in school. See, suppose I have taken a molecule like this. Organic, the little bit you have done in class 10. This is called butene. And see here. This is called, if they're in the same set of the double bond, we call them as cis. And if they're in the opposite side, we call them as trans. Okay, now see. How will you know which is cis and which is trans? We can find it from the melting point and boiling point that I'm going to discuss after some time. See here. In this case, this group, methyl group, supplies electron to this carbon. So this is the bond is polar. This also supplies this electron, the bond is polar. All right. And in this case, what is going to happen? This will be the resultant bond moment. So this molecule is polar. Okay. So it will have a dipole moment. It will have a dipole moment. So this will not be equal to J. But in this case, see here. This is in this direction, and this is in this direction. So they cancel each other. So here what we will find here, mu is equal to 0.0. The bond moments cancel each other. Okay.
That's
Okay. Now, see, with the help of dipole moment, we can explain the boiling point of the molecule as well as their chemical reactivity. The boiling point of chemical compounds and their chemical reactivities can be explained. So what we write now? Boiling point of depends upon their intermolecular forces of attraction, which is directly proportional to the polarity of the molecule. Okay, that is what the compounds which are more polar have strong attraction for other and have higher boiling points. See here, you have this and this. Here, this trans molecule is non-polar. So the boiling point of this molecule will be less than this. Example, trans butene. This is trans butene. Has lower boiling point than cis butene, as the former means this, as the former is former molecule has zero dipole moment.
Nah.
Okay. So this will be the part of the answer. So here you will write cis-butene, and here you write trans-butene. And you already written it, so now write this. When the molecules are polar, then they attract each other. When they're non-polar, they remain away from each other. So if they remain away from each other, boiling point will be less. Another example I'll give you. Okay, suppose you have taken here, you are not that much popular with this type of molecules, but anyway, see here. So this is called 1,2 dichlorobenzene, and this is 1,4 dichlorobenzene. See, if you compare their boiling point, write here boiling point, you'll find this is more than this. Why it is like this? See, in this case, carbon chlorine bond is polar. See, this is the bond moment, and this is the bond moment. One cancels the other. Okay? And this is the bond moment. This is the bond moment. This is the resultant bond moment. See here, the dipole moment of the molecule is not 0, but here dipole moment of the molecule is 0. So we can explain. 1,4 dichlorobenzene is non-polar. It is wide. 1,4,2 dichlorobenzene is polar. Thus, intermolecular forces of attraction among 1,2 dichlorobenzene molecules are stronger and have higher boiling point. we have discussed till now the ionic character of a covalent bond, bond or covalent molecule. Now we are going to discuss opposite. Covalent character of ionic compounds. This chapter is little critical, and you have to utilize a little of your common sense and general knowledge. See here. Now we are going to discuss that covalent character of ionic molecules. Right. So you know salts are soluble in water. But if you think that it is a judgment given by a court, everybody has to follow, then it's not wrong. You'll find that some salts are soluble in water and some salts are not soluble in water. But you know it very well. Moment I say salt, then it is an ionic compound. Then why it is not soluble? Because I had been telling you that whenever we make friends, we find you make friendship with them with whom many of your quality matches. The person who does have all the opposite qualities, you generally do not mix with them. So, as a famous saying is there, we call it like dissolves like. All right. So, why salts are soluble in water? Salts are ionic compounds, and now we have proved that water, though it is a covalent molecule, but it is highly polar in nature because of high dipole moment. Because of that, salts are soluble in water. If the question comes, why do ionic compounds are soluble in water, even though water is a covalent molecule? You're right, that water is a covalent molecule, no doubt, but it has very high dipole moment and is highly polar. Hence, ionic compounds are soluble in water. But you cannot say that all of them are going to be soluble in water. Why? Let us try to see. See here. Sodium chloride. Sodium chloride. Don't write. Highly soluble in water. Sodium bromide. Solubility is little less. Sodium iodide solubility is further less. Okay. Now I'll go for I'll write that example. I'll write here. Okay. Okay, this one I already given it. So now if you discuss or compare the solubility of lithium halides. Okay, if I write here solubility you'll find lithium fluoride is highly soluble. Lithium chloride is little less soluble. Lithium bromide is further less. and lithium iodide is least. Huh? So it is least soluble. But mind it, it is a salt. And interestingly, you will find lithium iodide is more soluble in non-polar organic solvents. Don't write organic solvents. But why should be soluble to organic solvents? Organic solvents are non-polar. Only covalent compounds are supposed to be soluble in organic solvents. It is a salt. It is Li plus and I minus. Why? Then people started thinking there may be something different which you cannot simply say on their ionic character. All right. So let's see. See here. This is a glass of water. Okay. Okay. So how many ways you can drink that water? How many ways you can drink this water? Huh?
Many ways.
I could not understand.
Many ways.
Tell me.
The straw.
Then, see, these are only 2 ways you can drink the water, not many ways. What will you do? What you will do? You will hold the glass and bring near your. You will open your mouth and tilt it, and you will pour the water inside your mouth. This is one way. Second is that with the help of a straw. So, moment you put a straw here, and if you suck, the water will rise. Water will rise and will enter your mouth. That is, you are sucking. That is, sucking means what? Sucking is nothing but attraction. So let me tell you. I'll give you 2 examples. See, I have taken lithium fluoride. Lithium fluoride, Li plus and F minus. In this case, lithium is having, what is this electronic configuration? 1s2, 2s1. Li plus means 1s2, 2s0. How it will look like? Look at it like fluoride. Fluorine is 1s2, 2s2, 2p5. F minus 1s2, 2s2, 2p6. See here, this outermost shell is empty. So this is lithium. This is the electron that you have here. And this is the shell is there, electron is not there. Okay. Now fluorine. This is, yes, we know, I already told you that the sizes of the anions are larger than that of the atoms. So now, This is the Lewis diagram of lithium fluoride. Fluorine, the size of the fluoride is much less than that of the, or smaller than that of the chloride, bromide, and iodide. Clear? So, I'm only going to draw the valential orbital of chloride, bromide, or iodide, anyone. So let me take here. Here it is. Lithium chloride. So it is lithium. Please remember the size of the chloride of lithium is double the size of chlorine atom. And see here. This is this one. This is see here. Here the size of the lithium ion is very small. Okay, and lithium has 3 proton inside. So its effective nuclear charge is very high. It has already lost. It wants to gain the electron. And this is the size of chloride, which is very, very large. So it has a large density of electron. When lithium goes nearby, it starts pulling the electron. Okay? When the electron will be pulled, then see, it is now, this chloride is having a homogeneous distribution of electron. Homogeneous. When the lithium goes near to it, it starts attracting the electron towards it. Just like that, when you put the straw inside the water, in that case, moment you start sucking, the water starts rising. Why? Because you have applied attraction. Then when the attractions, due to attractions, in that case, what will happen? Water will go up to this much. And when they are coming more and more close, attractions become bigger and bigger. Then in that case, what happens now here? See. Okay, now. In that case, moment the attractions become stronger, electrons are rushing. Now it does not become homogeneous. See, the thing which was earlier circular or spherical, now in one side the density of electron has increased. Another side has become less. See here now. Look. Earlier it was homogeneous, now it is not homogeneous. Electron has come more nearer to the lithium. Lithium is going closer and closer. Then in that case, what is going to happen? In this case, you'll find see now, just like the water has entered your mouth, in this case you'll find the electron of the chlorine has penetrated the empty shell of the lithium. We know overlap of the orbitals only can lead to the formation of covalent bond. See now, see, it has overlapped. So In that case, what is going to happen? That is overlap of the valence shell with electron takes place. Resulting covalent character. Now, because of that, you find the lithium iodide, though it is a salt, but it is having covalent character. And because of that, it is not going to solution in water. Okay, so let me remove this. Okay, right for this. This is this. No. After that, we'll write the statement. Write this. Then this.
Sir, done.
So let me write. When two oppositely charged ions of unequal sizes approach each other closely. When it will approach? During the formation of ionic mode. Otherwise, they will not come. Why should they come? The ion smaller in size. Smaller in size attracts outer, or what you can write, valence shell. Electrons of larger ion this result in distortion or polarization. Means one side electron has become more, other side has become less of the electron cloud. Of the bigger ion. This distortion is generally caused by cations, as they are, that we know already, sizes are smaller. Why their sizes are smaller? Because of high effective nuclear charge. Then Ni. The electron cloud of the anion no longer remains symmetrical, but is elongated. See, it has initially I have drawn it like this, later on I have drawn it like this. See here. This is symmetrical, this is elongated. Towards cation. The ability of a cation to polarize the nearby anion is called its polarizing power. Is called its polarizing power. The tendency of an anion to get distorted or deformed by the cation is called its polarizability. Where is my cloth? Oh, full stop. So right now, due to polarization, sharing of electrons. I told you, no, it is already entered the empty loop. Sharing of electrons occur between two ions. To some extent. And the bond shows some covalent character. Okay. So this is called depolarization of the. Okay. Okay, now. So now here the magnitude of polarization, next paragraph. the magnitude of polarization depends upon a number of factors. These factors were suggested by Hazan and is known as Fazan's rule. Don't forget the name of Fazan. Okay? Okay? Don't forget. All of you are very, very close to your father, huh? So you can remember him like this. See, this is your father. Okay? And here is his heart, and you are there. So you are this. Okay. So what are these factors? Who is going to attract more? If the size of the cation is small, nucleus is here because it's the nucleus which pulls the electron. If the size is small, attraction will be more. If the size is large, the distance from the valence shell, the nucleus increases, attraction decreases. So in that case, the size should be of the cation should be very small. And when you go for polarization, in that case, you'll find the size of the anion should be very large, because even in the valence shell, if it is 8 electrons are there, still nucleus controls them. If the size becomes very big, then nucleus lose the control. In that case, you will find these electrons can be pulled. That you have seen. When you are near your mother, people can influence you less. When you go outside the house, people can influence you more. All right? So, in that case, 1. Size of the cation. Polarization of the anion increases as the size of the cation decreases. That is, the electrovalent compounds having smaller cations show more covalent character. Okay, say I have taken here this example. Covalent character. See, group 1, what do you have? Lithium, sodium, potassium, rubidium, and cesium. I'm not writing francium because francium is radioactive. So when you go down the group, what happens? Size increases or not? So this is having the smallest size, this is the largest size. So this one is going to polarize more. So what I can write now here? Lithium chloride will be more covalent than sodium chloride. Sodium chloride will be more covalent than potassium chloride. Potassium chloride will be more covalent than rubidium chloride. And rubidium chloride will be more covalent than cesium. See, because why does it cation attracts? Because they are electron deficient. So we can have cations like, see, I can have cation like this. I can have cation like this. I can have cation like this. So where you will have more attractions? As the number of positive charges increases. As the number of positive charges increases, nucleus wants more and more electron. It becomes more and more hungry. All right. So in that case, the second one. Charge on cation. As the charges on the cation increases, its tendency to polarize the anion increases. This brings more covalent nature in electrovalent compound. here. Example क्या होगा? AlCl3, see it is Al3 plus, is more covalent than what should I write? BeCl2, B2 plus, and this is NaCl. B नहीं होगा रे. Same, I have taken from same period. MgCl2. Don't write this photo. Finish.
Yes, sir.
আজকে তোর কিটা ক্লাস শুরু হইব নাকি স্কুলে? হ্যাঁ?
Yes, sir.
তোরা কিটা স্কুল দি See, when n become larger and larger, then distortion is more. So, the larger the size of the anion, more easily will be polarized by the cation. That is, as the size of the anion increases for a given cation, for a given cation, the covalent character increases. Okay. Example, covalent character. Now see here. I have already given you this example earlier. See, as you go down the group, sizes of the atom increases. When the sizes of the atom increases, the anion becomes almost double, bigger. All right. So I'll write down here lithium chloride, lithium chloride, lithium bromide, lithium iodide. See, these are largest size, so it will be most covalent. So it is ulta.
Yes,
What about
sir.
other? Okay, the last one. 4 is configuration of cation. Configuration of cation. Okay, we'll write here. Or pseudo. You know the meaning of pseudo? Hello?
No, sir.
No, sir.
False.
pseudo মানে জানিস না? মারিয়া ঠান্ডা করবো। Pseudo means fake. Inert gas configuration. See, what is inert gas configuration? Inert gas configuration is NS2 NP. NS2 NP6 means its inert gas configuration is octet 8. It is NS2 NP6. Now, what is pseudo inert gas configuration? Where you find S, P, and D orbitals all filled up. What is the maximum number of electrons on S? 2. P, 6. D, 10. Right now, the cations with 18 electrons right now we have NS2, NP6, and D10. In is valence shell brings a better greater দ্বারা আমি তোমার 2 মিনিটে ক্লাস শেষ greater polarization
I completely agree with that. Yes.
of the anion. Then those with inert gas configuration. See, this is inert gas. Even if both the cations have same sign and same charge. Okay, example you will find here. Covalent character. See here, CuCl is more covalent than CuCl2. Why? In this case, you have here CS2, TP2, sorry, TP6, DD10. And this is CS2, 3p6, 3d9. This is not soluble in, this is not soluble in water, it's soluble in water. Not soluble in water and soluble in water. Okay? AgCl, not soluble in water. But it is a salt. Why? This is having 4s2, 4p6, and 4d. Bye for today. This chapter